So it turns out there's this really big and frankly super expensive inefficiency hiding deep inside pretty much every large language model we use today. And there's a new architecture, it's called Engram, that's designed to fix it. This isn't just a small tweak either. It could be a huge shift in how we build AI. Okay, so here's how we're going to break it down. First, we'll dig into that hidden inefficiency I mentioned. Then we'll look at the big idea behind Engram, get into the nuts and bolts of how it works, and check out the pretty wild performance gains it gets. And finally, we'll zoom out and see what this all means for where AI is headed.
All right, first up, AI's hidden inefficiency. The bottom line is every single LLM out there that's built on the transformer architecture, and that's basically all of them, has this one major problem. They are just incredibly wasteful when it comes to computation.
You see, we ask these models to do two totally different kinds of jobs, right? On one hand, you've got really complex reasoning, like explain the geopolitical factors behind World War I. On the other hand, you have simple fact-checking, like who was the first person on the moon. The problem is, right now, our AIs use the exact same super complex, energy-guzzling machinery for both tasks. It's like using a supercomputer to do basic addition. And that is the core inefficiency we're talking about.
Let's make this concrete. Just to identify Diana, Princess of Wales, a model has to basically rebuild that fact from the ground up, every single time. It's not just looking it up. Its first layers might have to figure out, okay, Wales is a country in the UK. The next layer adds, all right, that's in Europe. Then another layer realizes Princess of Wales is a royal title. It's only after all these computational steps that it finally pieces everything together. It's an unbelievably roundabout way to get to a simple piece of stored information.
So this whole mess comes from one core mistake. We're treating memory and reasoning as if they're the same thing. But here's the cool part. The clue to fixing this has actually been hiding in plain sight, inside the transformer architecture this whole time. Researchers figured out that some parts of the transformer are already, trying their best to act like a memory system. Those feed-forward layers, they work almost like a key-value memory. They spot a pattern, that's the key, and then they spit out the associated information, that's the value. The model is basically trying to imitate a simple dictionary lookup, but it's using its super expensive reasoning brain to do it. It's a hack. And that's when you have the big aha moment. Instead of forcing the model to fake having a memory using its complex reasoning circuits, why don't we just give it a real memory system? And that right there is the core idea behind the Engram architecture. It's all about one thing, separating recall from reasoning. So what Engram does is it adds a whole new dimension, a new access to the model, which they call conditional memory. Think of it like this. It creates a totally separate parallel highway for information to travel on, a highway that's built just for fast fact retrieval. This really changes the whole internal layout of the AI.
And here's how those two pathways look side by side. On the left, you've got your traditional conditional computation, which you might know from mixture of experts, or MO models. That's the slow, heavy thinking lane. It sends really complex problems to specialized expert circuits. But now on the right, you've got Engram's conditional memory. This is the express lane. It zips simple requests for facts over to a giant, super fast lookup table. For the first time, we're actually using the right tool for the right job.
Okay, so how does the system actually know which lane to use?
Well, the secret sauce, the most important part of this whole thing, is a component called the context-aware gate.
The process is actually pretty clever and simple. First, the system scans the text and picks out common little phrases, or engrams. Then, it turns those phrases into a unique digital fingerprint, a hash, which is basically a super fast pointer that leads directly to an entry in a massive memory bank. Poof, the information is retrieved instantly. But here's the genius part. A smart gate then looks at that retrieved memory and asks, hey, does this actually make sense right now? And that gate is what makes this whole system work without messing everything up. It gets the context. So if you're talking about Apple Inc. stock, the gate is like, yep, makes sense, and it lets the memory about Apple the company through. But if you're talking about a fruit salad recipe, the gate sees the word Apple, looks at the memory for Apple the company, and goes, nope, that's not right, and it blocks it. It prevents the AI from making really dumb, out-of-context mistakes. Okay, the big question, does this actually work in practice? Well, the results aren't just good, they're genuinely surprising, and they hint that something much more profound is happening under the hood. So, no surprise here, if you give a model a better memory, it gets better at knowledge-based tests. We saw big jumps, like 3 or 4 points on major benchmarks. That's great, that's what we'd expect. But the thing nobody saw coming was what happened with tasks that are all about pure reasoning. This is kind of wild. The model's reasoning skills actually got better than its knowledge recall did. We're talking improvements of up to 5% on some key reasoning benchmarks. That's a huge deal. It completely goes against what you'd think would happen, and it proves that just offloading memory does way more than just speed up lookups. So what's going on? The researchers call it becoming functionally deeper. Think about it. In a regular model, those first few layers are completely bogged down just trying to piece together basic facts. They're wasted. But with Engram, that memory lookup is instant. It's done. That means every single layer of the neural network from top to bottom can be dedicated to its real job, actual, deep, complex thinking.
And the wins just keep coming, even down to the hardware. Because the memory lookups are so predictable, the CPU can grab them ahead of time with almost zero performance hit. This is huge because it means you can have these massive 100 billion parameter memory tables sitting in regular, cheap system RAM, not the super expensive VRAM on your GPU. It also helps with long context stuff because the model's attention isn't getting distracted by simple facts and can focus on the big picture connections in a long document.
All right, let's zoom out for a second, because this whole idea, this splitting of jobs, it's not new. In fact, it's a pretty good mirror of a famous theory about how our own brains work. We humans are often described as having two systems of thinking. There's System 2, which is our slow, deliberate, effortful brain. That's what you use for a tough math problem. And then there's System 1, which is fast, automatic, intuitive, like instantly recognizing a friend's face. Well, Engram basically gives AI that same two-brain setup. You've got the deep computation for System 2 and the instant memory lookup for System 1.
At the end of the day, the core idea here is incredibly simple, but also really profound. For years, we've basically been using a super powerful calculator to store phone numbers. Sure, it works, but it's a ridiculous waste of resources. Engram finally gives the AI an address book. It provides the right tool for the job, giving it a natural, efficient way to manage memory. And based on the results we're seeing, it looks like this might just be the component that these models have been missing all along.